When you hear the phrase instructional technology, your brain likely jumps straight to the hardware, smartboards, tablets, or virtual reality headsets. But to actually understand how we optimize human learning, we have to establish a strict rule right now. The physical device is not the instruction. In the context of pedagogy, hardware is merely a delivery mechanism. It is the conduit. The foundational definition of this field actually comes from the 1970 Commission on Instructional Technology. They defined it not as a collection of devices, but as a methodical approach to planning, executing, and assessing the entire teaching and learning process. This methodical approach does not stem from computer science or IT. It is rooted entirely in applied behavioral and physical sciences. Today, we are going to build an accurate mental model of instructional technology by severing the physical mechanisms from the systemic design behind them. Confusing a delivery mechanism with the actual science of instruction is exactly why schools can spend millions adding expensive screens to a classroom only to see zero improvement in student outcomes. To organize this field, instructional technologists divide the world into a strict duality: hard technology versus soft technology. Think of hard technology, the screens, the software, as a grocery delivery truck. Its only function is to transport a payload to a destination. Soft technology is how the cargo itself is engineered, the specific nutritional value packaged inside, tailored specifically for the learner. Precisely defined, soft technology consists of the instructional strategies, design procedures, and methodologies derived from behavioral science. The ultimate proof of this separation is that an expert teacher can flawlessly execute soft technology, like running a highly structured debate or applying behavioral shaping, without using a single piece of hard technology. Upgrading to a faster, shinier delivery truck accomplishes absolutely nothing if the instructional nutrition inside the payload is flawed. So how do we engineer that soft technology payload? We start with its first foundational axis: the systematic approach. This is a deliberate, sequential technique for solving instructional problems. It operates on a strict linear path: identify the problem, analyze, solve, implement, and evaluate. But one paramount rule exists: the final target behavior must be explicitly defined before the start. Without a highly defined behavioral goal, a systematic method has no direction. It is useless. This linear, goal-oriented thinking stems from mid-20th century behavioral psychology, heavily influenced by operant conditioning theorists like B.F. Skinner. By applying these concepts, behavioral technologists use techniques like shaping. They analyze the gap between a student's current behavior and the target behavior, and break that gap down into tiny, incrementally reinforced steps. The systematic approach is the engine of instructional design. It guarantees that instruction is goal-oriented, moving the learner logically from their baseline directly to the objective. However, relying purely on linear systematic design introduces a critical flaw. Human education does not happen in a sterile vacuum. This flowchart illustrates the second axis, the systemic approach. External forces, factor A, factor B, factor C, constantly impinge upon the linear steps. Because these variables are interconnected, altering one single node inevitably impacts the surrounding nodes and final outcome. We can observe the tension between systematic and systemic goals in a real-world manufacturing case study. A factory was struggling with ineffective training because it relied on large group classroom lectures for its new hires. The workers lacked hands-on experience. Management implemented a strictly systematic solution. They pulled their top 5 performers off the factory floor to conduct intensive, one-on-one, on-the-job training. The training itself worked beautifully. The new hires learned quickly. But it was a systemic failure. Overall factory production dropped because the company's best workers were busy teaching instead of manufacturing. A brilliantly designed systematic intervention will ultimately fail if the instructional designer ignores its systemic impact on the adjacent operational and cultural factors. The practical, classroom-level execution of merging systematic rigor with systemic awareness is known as differentiated instruction. It is commonly misunderstood as a simple classroom management tactic, or merely giving students a choice of homework assignments. In reality, differentiated instruction is the rigorous structural engineering of the curriculum itself. It dynamically splits into tracks built and filtered based on 3 specific learner variables: a student's readiness, their unique interests, and their learning preferences. The engine that makes this systemic differentiation possible is continuous data feedback loops, better known to educators as ongoing assessments. These assessments dynamically route students to the correct instructional intervention in real time, whether that requires a small group problem-based exercise or highly individualized software. Yet despite students taking entirely different paths, the systematic goal remains rigid. All students must hit the exact same stringent curriculum expectations. True differentiation proves that the highest level of instructional technology is invisible. It is the architecture ensuring distinct paths converge on the same high standard. This brings us back to our starting thesis. Instructional technology is the process, not the processor. We have to package the systemic network complexity into our soft technology cargo well before we ever load it into the hard technology delivery truck. This completely redefines the role of the modern educational technologist. They are not IT support specialists deploying tablets. They are high-level architects of human behavior and cognitive absorption. We certainly have access to incredible new delivery systems, like AI and adaptive algorithms, but those tools are completely dependent on the underlying behavioral framework driving them. By mastering the interplay of hard and soft technologies and balancing systematic precision with systemic awareness, we move past the illusion of hardware progress. We build invisible systems that actually optimize human learning.